Good day. My name is Michael Rooks. I'm coming to you from Port Orange, Florida. Accuracy and precision with the bow requires a consistent shot cycle, steady aim, and a well-tuned bow. Today, we will look at what goes into tuning a bow, not the how-tos, but the whys. What is the physics behind the recommendations? Specifically, we will look at the physics of finger release as opposed to mechanical releases. We will be talking about single string bows, but much of the information is applicable to compound bows. The elements of bow tuning can be condensed in categories of arrow spine, static and dynamic, brace height, center shot, nocking point placement, and bow tiller. When the bowstring is released, several forces are placed on the arrow. The downrange force is what delivers the arrow to the target. However, slippage of the string on the fingers will produce a lateral force away from the bow to the left in a right-hand shooter. This force will produce vibrations in the arrow and a torque rotational force towards the bow. The initial torque will be counteracted by the plunger or pressure plate on the sight window. The interactions between the string and arrow will continue until the arrow leaves the bow. A vibrating arrow will have two nodes where there is no vibration. These nodes define the path of the arrow. The point, middle, and tail of an arrow will vibrate back and forth perpendicular to this path. Weaker, more flexible arrows vibrate slower with a higher amplitude than stiffer arrows. The vibration does not affect the arrow path if no contact with the bow occurs. However, rotational or torque forces produced by the string will change the alignment of these nodes and the direction of flight. The string has a higher natural vibration frequency than the arrow, and this interaction combined with the arrow's frequency of vibration determines torque forces. In a well-tuned bow, the arrow will vibrate approximately 1 1/4 cycles before it passes the riser of the bow. This assures that the flexed end of the arrow is flexed away from the riser when it passes. If the opposite were true, then the back end of the arrow could make contact with the bow. This would produce erratic arrow flight and possible damage to the bow, arrow, archer, or all of the above. Ideally, the arrow should leave the bowstring at the end of the first cycle. If the arrow is too weak, it will not complete this cycle before leaving the string and will result in a cumulative torque to the right. A too stiff arrow will be into the next cycle with a cumulative torque to the left. The stiffness of an arrow is called its spine. Clearance is accomplished through the static spine of an arrow. Each arrow manufacturer will produce a chart showing the appropriately spined arrow for a given bow type, recurve, longbow, or compound, a given draw length, point weight, and a given draw weight or poundage. If the spine is too high or too low, contact between the bow and arrow can occur. The spine of an arrow is usually determined by the ASTM testing standard. A 29-inch arrow is supported at 2 points 28 inches apart. An 880-gram weight, 1.94 pounds, is suspended from the center of the arrow. The deflection is recorded in tenths of an inch and multiplied times 1,000. Deflection of 0.500 inches gives a static spine of 500. The lower the spine, the stiffer the arrow. There is an older ATA, Archery Trade Association standard, that uses a 907-gram, 2-pound weight and 26-inch separation. This is generally used only for wooden arrows. The STM standard is slightly weaker than the ATA standard. Longer draw lengths and higher poundage bows require stiffer arrows, lower spine number. Stiffer arrows, lower spines, vibrate more rapidly. Too low or too high a spine can result in bow contact, sometimes catastrophic, and poor flight. A stiffer spine, lower number, is always safer than a weaker spine, higher number. The static spine comes in 1/10 inch increments. The dynamic spine of an arrow is the adjusted spine that gives proper flight downrange. If the spine is a little too stiff, the arrow will fly to the left; if too weak, to the right. Factors affecting the dynamic spine include exact draw length, release consistency and grip, actual bow poundage at release, Spine can be stiffened by shortening the arrow, a lighter point weight, a heavier knock pins or bushings, or when possible, by lowering the bow poundage. With an adjustable bow poundage, this is usually the first step. Changing the arrow points is next in line. Further fine-tuning adjustments in dynamic spine can be accomplished by varying the center shot. Brace height is the perpendicular distance from the notch and the bow grip to the string and a strung bow. Proper brace height requires the proper string length for the bow length. Strings are 3 to 4 inches shorter than the bow and based upon manufacturer recommendations. Recommended brace height ranges are also provided by the manufacturer. Brace height can be tuned to the ideal length by twisting and untwisting the string. Brace height is set to optimize knock separation from the string. We have seen that the arrow will oscillate 1 1/4 cycles before it leaves the bow. This is the same as 5 quarter cycles. If the brace height is set ideally, the knock will leave the string at the junction of the fourth and fifth quarter cycles. With regards to timing, the arrow will reach maximal speed as it leaves the string and continue at pretty much the same speed past the sight window. We will assign this interval as 1 unit of time. If the brace height is 1/3 of the draw length, the arrow will travel from 0 to the exit speed at an average of approximately 1/2 that speed, or in 2 units time. This is assuming acceleration is linear. It will also have to travel twice as far, 2 times 2 or 4 units of time. This 1 to 4 ratio aligns with the 5 cycles in the arrow vibration if the cycle rate is constant. In this theoretical situation, the brace height would always be 1/3 of the draw length. However, we know from force curves that the acceleration is never linear, and the same is likely for the arrow cycle rate. The ideal brace height for a given setup can only be determined through trial and error. The best brace height will give the least amount of vibration and bow noise on release. If a recommended brace height is 8 to 9 inches for a 27 to 29 inch draw, and I had a 28 and 1/2 inch draw, I would start it a little longer than the halfway point, 8 1/2 inches. The third element in tuning is center shot. This is the right to left alignment of the arrow rest and plunger/face plate or cushion. The bow is positioned so as to align the string with the center of both limbs and the riser handle. An arrow is knocked to the string and placed on the rest. The point of the arrow should align just slightly to the left, right-handed archer, from a dead center on the spring. This is the ideal spot for a perfectly spined arrow. Mild spine inconsistencies can be corrected with center shot adjustments. Moving the point to the right will weaken the dynamic spine and move the flight to the right. Nocking point placement is one of the poorer understood elements in bow tuning. When the bow is drawn to anchor, the pivot point of the bow is actually in the grip of the bow. The arrow rest and perpendicular nocking point are on the order of 3 to 4 inches above this in a standard target recurve. This results in a downward force on the knock at release. This downward force will bow the arrow center up and rotate the arrow point up. The lack of a restraint to the upper rotation of the point can result in inconsistent flight. The arrow oscillations are also predisposed to tail-end contact with the arrow rest or sheath. This problem is further accentuated by rotation of the bow upper limb towards the archer, secondary to the arrow inertia and the low pivot point. A third element will also contribute to these undesirable torque and oscillation forces. Because of the angle of pull from the grip to the nocking point, there will be more tension force in the lower portion of the string than the upper. This will result in more flexion of the lower limb and elevation of the nocking point. This will increase the effects noted above. In concert with the title of this presentation, I will go through the math for this claim. It requires a little high school trigonometry and linear algebra. If math scares you, feel free to fast forward. Angle theta is the angle between the arrow rest and the grip at full draw. Arc sine theta is equal to the height difference from the grip center to the arrow rest divided by the draw length. The horizontal x and vertical y components of the draw force can be calculated using theta. X equals the cosine of theta times the draw force, and y equals the sine of theta times the draw force. Angle theta 1 is the angle between the upper string and arrow at full draw. Angle theta 2 is the angle between the lower string and arrow. Arc cosine theta 1 is equal to the draw length from the line between the bow tips to the nock divided by the upper string length. Arc cosine theta 2 is equal to the draw length from the line between the bow tips to the nock divided by the lower string length. Theta 1, theta 2, x, and y are used to compute the string tensions T1 for the upper string and T2 for the lower. T1 and T2 are resolved into horizontal forces x1, y1, and x2, y2, respectively. x1 plus x2 equal x. x1 equal cosine theta 1 times T1. x2 equal cosine theta 2 times T2. Therefore, cosine theta 1 times T1 plus cosine theta 2 times T2 equal x. And T1 equal x minus cosine theta 2 times T2, all divided by cosine theta 1. y2 equal y1 plus y. y1 equals sine theta 1 times T1. y2 equals sine theta 2 times T2. Therefore, sine theta 2 times T2 equals sine theta 1 times T1 plus y. And T2 equals sine theta 1 times T1 plus y, all divided by sine theta 2, with substitution of T1 equals x minus cosine theta 2 times T2, all divided by cosine theta 1. T2 equals sine theta 1 times x minus cosine theta 2 times T2, all divided by cosine theta 1 plus y, all divided by sine theta 2. Rearranging terms to get T2 on the same side gives us T2 equals sine of theta 1 times x divided by cosine theta 1 times sine theta 2 plus y divided by sine theta 2, all divided by sine theta 1 times cosine theta 2 divided by cosine theta 1 times sine theta 2 plus 1. The value of T2 is used to solve T1. T1 is equal to x minus cosine theta 2 times T2, all divided by cosine theta 1. Sample calculations with one of my bows gave a lower string tension force 8% higher than the upper string. This knocking point effect can be reversed by raising the knocking point relative to the arrow rest. 1/4 to 3/8 of an inch is recommended. Some recommend a 1/2 inch for bare bows. This changes the vector forces on the nock, producing a downward bowing of the arrow center and down rotation of the point. The arrow rest helps restrain the rotation as seen with the lateral rotation. Tail contact with the rest is minimized. Tuning of the knocking point is aimed at minimizing vertical torque and oscillations without reversing their desired direction. The final element in our list is bow pillar. Pillar is the perpendicular measurement between where the limb meets the riser and the bowstring. If the tiller measurement is higher at the upper limb than the lower, then positive tiller is present. If equal, neutral tiller, and if less, negative tiller. Neutral to 3/8 inch positive tiller is recommended where limbs are adjustable. A positive tiller increases the poundage on the lower limb and limits the knocking point rise at full draw. Recommendations: 1. String your bow and set your brace height at your best guess based on your draw length and manufacturer recommendations. 2. Check your limb alignment and if possible, unstring and adjust and restring. 3. Set your center shot slightly left of dead center. 4. If shooting split fingers, set your nocking point at 3/8 of an inch. Slightly lower if you adjust to a positive tiller. If shooting 3 fingers below, closer to a ½ inch. 5. Shoot the bow. 6. Try to set your spine first with bow limb adjustments, if available, and then with point weights. Be cautious with center point adjustments. The spine does not have to be perfect to shoot 10s. 7. When you can group well on a 122 centimeter target at 20 yards, it's time to look more closely at nocking point adjustments, dynamic spine adjustments, and brace height changes. It's time for barrel shaft tuning. Any reasonably tuned bow will outshoot the average archer. The initial effort should be on a consistent, repeatable shot cycle and steady aim. Those crazy shots aren't the bow. When you're ready for serious tuning, you'll know it. If you have made it to this point, congratulations are in order. Thank you for your time and your attention.